We've looked at adding complex numbers, now we're going to look at multiplying complex numbers. So these are two complex numbers that I'm going to multiply together. And first thing I want to say is that I know what your temptation is when you multiply these together. You want to use FOIL, right? What I mean by FOIL, what I mean is, you know, when you multiply binomials, I'm sure many of you use what's called FOIL, by which you multiply the fronts here and then the outers. Or I think I'm even messing it up here. You multiply the first and then the outers here, and then the inners, and then the last. So the reason why I don't like FOIL is because it's actually, FOIL is not really a mathematical idea. It's not an operation or anything. All it is kind of a shortcut to help kids remember how to multiply binomials. But it doesn't work. It does not work if you have to multiply something like this. If you have to multiply like x squared, or x plus 3 times x squared plus x plus 2, right? FOIL doesn't work because you have a bunch of inners and outer products, right? It's just not so straightforward. So there's a better way to view multiplication as opposed to FOIL. So, and that's viewed as the distributive property, because that's really what's happening. So if I have like 3 times x plus y, we all know that that's just 3x plus 3y, right? And so that's how I'm going to do this multiplication here algebraically. I want to view my 1 plus 3i as like my 3 above, and I'm going to view this 1 plus 2i as like my x plus y above. And I'm going to distribute. So algebraically, so this is the algebraic representation of multiplying these two numbers. So algebraically, let's distribute the 1 plus 3i. So first it would be distributed to the negative 1. So I get 1 plus 3i times negative 1. And then I do plus 1 plus 3i times 2i. Now this is an important step which we're going to use over here eventually when we do this geometrically. But so I'm going to just like underline it in pink. But let's just continue the problem here. So 1 plus 3i times negative 1, at this point we know you can distribute the negative 1 as well. Negative 1 and then negative 1 times 3i is negative 3i, plus 2i times 1 is 2i, and then 2i times 3i is 2 times 3, which is 6. I times I is I squared, which is negative 1, so it's 6 times negative 1, so it's negative 6. And now we add up the real parts and the imaginary parts to get our final answer of negative 7 minus I. What about geometrically? How do we interpret this multiplication geometrically? Well, it's a little bit more difficult to view it geometrically if we start here. Since we're in 2 dimensions, multiplying these complex numbers, there's a lot of things going on, because not only are you like scaling the numbers, meaning like changing their length, or I should say vectors, we're going to view these as vectors. Not only are you changing the vector's length, you also have these i's in here, and even that negative 1, which affects the direction, right? We know those have the effect of rotating. So that is hard to keep track of in this step here. But here, once we do that initial distributing, we've basically turned a multiplying problem into an adding problem, and we know how to add vectors and complex numbers, since we saw it in the last video. So this is after you distribute, this is the key step where you can actually do the geometric representation. So watch how it works. Here's my 1 plus 3i times negative 1. So let's start with 1 plus 3i. We know We know that's my imaginary axis. There's my real axis. We know that 1 plus 3i looks like this. But multiplying it by -1 causes it to rotate 180 degrees without changing its length. And so it's down here at -1 minus 3i. And of course, that's what you get when you distribute. But geometrically, we know that this is 1 plus 3i multiplied times that -1. Right? It's 1 plus 3i rotated 180 degrees. Now let's go over to the 1 plus 3i times 2i. So first of all, it's 1 plus 3i times this 2. So what does this 2 do? The 2 here is going to double the length of 1 plus 3i. And then this I, we know, is going to rotate it 90 degrees counterclockwise. So how do we depict that? Well, we start with 1 plus 3i. Here's my 1 plus 3i. That multiplying by 2 is going to double it. So now it's up here. So I just doubled its length, same direction. And now I get to rotate it 90 degrees counterclockwise. So this is where you kind of have to use the slope notion, right? What's the slope of this orange line right now? It's, well, it's 3 over 1, right? And so, or you could view it as 6 over 2. And so if I want to rotate it 90 degrees counterclockwise, I want the line that's perpendicular to it, that's over here somewhere. And that means that I have to graph the line that has a slope of, well, let's see, the opposite reciprocal of 6 over 2 is -2 over 6. And so let's do a little testing here. So here's my 6 plus 2i. So I need to rotate this so that its slope is down to right 6. And this does it. Right? So there is, after all that, this here is my 1 plus 3i times my 2i. Just checking here. Yep. Okay, and again, I'll put it like in like really light yellow what the original was, so you can see that it's indeed 90 degrees there. Right, and this slope here, right, the slope of that guy was 6 over 2, and we notice that the slope here is -2 over 6. All right, so these are the results of those separate multiplications here. But I am adding those two vectors, right? I'm adding this vector to this one. And so that means that, well, how do we add vectors? We add them by doing the tail to head method. So here is 1 plus 3i times 2i. What I'm going to do is I'm going to move it down. I'm going to move it down. And since I know you can't move it, I'm just going to actually redraw it. Move it down so that its tail is here. And I've got to go left 6 and up 2. And I get my final answer. Right here. There is, what is it? It's -1, 2, 3, 4, 5, 6, 7, -7 minus 1i. All right. So what would you have to show it, to show me that you knew the geometry? You wouldn't have to show this line right here. So I'll erase this. You would just have to show. First, you would distribute. Okay, you just do that distribution to make it look like two vectors that are being added. Then you want to actually graph this complex number and its rotation or whatever effect that this number has on it, which we did here. You'll want to graph this one and whatever rotation or transformation that's implied from this number here as well. And then you add them by doing the tail to head method. And we have our final answers, -7 minus 1i, which is precisely what we got when we did it algebraically. Alright, so there is complex numbers and how you add them geometrically. And it may seem like this is a long-winded way to do it, but there are advantages to viewing complex number multiplication and addition geometrically, which we'll talk about later. But there is a reason behind this madness, and so hopefully you get a good understanding now of how complex number multiplication can be viewed geometrically and algebraically.